It would look something like this, you guys.
All right. Turn on your peeking tabs. Is it gonna be like apps greater than or equal to graph things?
Well, it'll look like that, but
Okay. Yeah.
that's exactly what it is. Yep. What's that? Well, so if we're trying to find this area right here, that would be the area between two curves. Now Danny had a pretty good idea, and she's absolutely right. Let me do this in some different colors here. Let's see. So guys, the area underneath F itself would be from F all the way down to the x-axis. This would be the area under F. You guys agree?
Yes, sir.
Now, if we did the area under G, that would be this area right here. This is the area under G.
Yes, sir.
So, if we wanted to find the area between F and G, you take the area under F and then you subtract the area underneath G. And that's the area between two curves. Okay?
Oh my.
So, write down this formula. Area equals the integral from A to B of f of x minus g of x dx.
Okay.
It's really easy. You just take the area underneath one curve and subtract the area underneath the lower curve.
Yeah.
So you have to be given two bounds of integration. And listen, two things you need to know. The bounds of integration. Here it's obviously A and B. You also need to know which function is above and which function is below. Okay? And it's not always explicitly stated. I mean, if we have a picture of it, yeah, it's easy. Obviously, f is the function above, g is the function below. Problem? But if we're just given equations and no graph, we're going to have to be able to tell which function is above, which function is below. And we may have to also find the bounds of integration ourselves. But usually these are pretty straight up problems. Okay? So here's an example.
So what if it were like saying word for word, but you still
As long as you had two bounds. Yeah. Like this one here. Because we're not finding the area between intersection points.
What if
the
they
area between the bounds.
oscillates?
Ooh. We'll do an example. A couple examples like that. Okay, find the area of the region bounded, yes I am, thank you, bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. Initially, it might help you guys to see a picture of this. You'll probably get to the point where graphs don't even matter and you don't need them, but just because this is new, let's try to draw a graph of the situation. X squared plus 2. It's a parabola. Where's the parabola? The vertex is up 2 units, and it's facing up. It looks something like that.
Okay. This is the graph of x squared plus 2. What about y equals negative x?
Oh, it's going to be a diagonal slant right through the origin.
With a negative slope of negative 1. So this is the graph of y equals negative x.
We're going from 0 to 1.
Hey guys, just so you don't get confused, these last two equations, x equals 0 and x equals 1, those are just vertical lines. So we have a vertical line going through 0, and we have a vertical line going through 1. You guys with me on that?
Yeah.
All that means is that's the left and right sided bounds of our region, and the upper and lower bounds are this parabola, and the lower bound would be this y equals negative x. So the region we're trying to find is from the y-axis over to this line, and then up to the parabola, and all the way down to this line right here. You guys?
It says to try to go out this time, right?
No, we still use the same formula. You guys see that region there?
Yeah.
Now looking at the graph, which of the two functions? So the integral is going to be from 0 to 1, but what function do we start with? We start with the x squared plus 2, because that's the above function, quote unquote. It's the function that forms the upper part of the region. And then you subtract the function that forms the lower part of the region.
Because it's going to be negative, so you subtract.
So you subtract negative
Oh, yeah.
So it's going to be
x.
So I was like, so that only goes from there and that one only goes from there. So
And then you take the integral. You guys follow?
Yeah.
I'm telling you, for the most part, these are pretty straight up questions. They're not that difficult.
that simple.
Most of them are.
Here comes the but.
No, most of them are. What's the antiderivative here?
the antiderivative is going to be
X to the third over 3
plus 2x
plus 2x.
minus
Plus.
And then we just evaluate that from 0 to 1.
Okay, that wasn't too difficult.
And we're going to use our fundamental theorem of calculus.
Absolutely. So the fundamental theorem says you do the antiderivative of the upper bound minus the antiderivative at the lower bound.
You were gone.
So the antiderivative at the upper bound is 1/3 plus 2 plus 1/2. Ooh, nice. What's the antiderivative at the lower bound? That's just a big fat 0.
Good. I like it when it's like this.
Oh, man. 1/3 plus 2 plus 1/2.
I like it when it's easy.
That's 5, 6. 2 and 5, 6.
Yeah, it's going to be 2 and 5, 6. Yeah. You're right. This would be 2, 6 plus 12, 6 plus 3, 6, which is 15, 17, 6.
It's actually my favorite number. How do you know?
Which is 2 and 5, 6. And that's it. That's all the lesson.
Yeah.
No.
Let's move on to the last lesson. The April Fool's stuff.
April Fools! Wouldn't that be so awesome?
Yes.
No, honestly though, this lesson and the next one, we're ending on relatively easy lessons. These are the last 2 lessons of the entire curriculum.
Never thought we'd make it at this point.
Isn't this about the time college finals are going on?
Yeah, well, 3 more weeks.
3 more weeks?
Yeah.
So we're following a college curriculum almost.
Pretty much.
Nice.
Find the area bounded by f of x equals 2 minus x squared and g of x equals x. They have not given us as much information here on this problem. Do you notice what's missing?
the bounds. What that means is these graphs intersect to form natural boundaries on the left and the right. If that makes sense.
Like what we saw before, this sort of.
Yeah.
Do you guys remember when we were just trying
Check it
to
out.
point the-
That graph I drew earlier, you see how these graphs kind of form natural boundaries here and here?
Yeah.
That's what's happening. That's what's happening here. Okay? So, again, we don't necessarily have to graph this, but might as well. 2 minus x squared.
You're gonna go up to.
We're going to go up to, there's the vertex. But this time the parabola faces upside down because it's negative x squared. You following?
Yeah.
So this is the f function. And then g of x equals x, that one's easy. It's just a 45-degree angle line going through like that. This is the g function. So you can see that these two graphs form natural boundaries on the left and the right.
I think the right one's at 1.
So we need to find the actual coordinates here. What's that coordinate and what's that coordinate?
The one on the right is 1.
Yeah.
Allow me to explain how I know.
Yeah.
Yeah, this is something you guys did back in pre-algebra and algebra 1 and algebra 2. To find the intersection of two graphs, all you do is set the equations equal to each other. 2 minus x squared equals x. If you set the two equations equal to each other, then you'll find their intersection points. Huh?
Unless they're not determined x. I mean y.
So if we rearrange this and get one side equal to 0, we're going to have 0 equals x squared plus x minus 2. And we are so lucky. This factors.
And x minus 2.
Into
X plus 1.
x plus 1, x minus 2.
No, it's x minus 1, x plus 2.
Or is it x minus, hold on now, x,
No,
you're
it's
right, x
minus-
minus 1, x plus 2, there we go. So then x equals 1, x equals negative 2. Now, matter of fact, we don't really need the full coordinate. We just need to know the x values of the coordinates. This is an x coordinate of 1. That's an x coordinate of negative 2. Okay, and those are our bounds of integration. So we don't actually need the y part of those coordinates. Do you understand what I'm saying?
Yeah.
You can find them if you wanted to, but we don't need them. So those form the bounds of integration. So we're taking the integral from negative 2 to 1. And according to this graph, the f function forms the upper region of this. So we're going to take that one first, 2 minus x squared. And then we subtract the graph that forms the lower region.
Will a calculator do this?
Yeah. So if you type in 2 minus x squared, and then for the g function, you know what, actually, let's see. You know, I'm not sure, we could try it. So there's one graph, there's the other one.
I don't know how to get rid of those lines. Those slope fields.
Oh, the slope field's still on there?
Yeah.
I'm not sure either. I'll have to come over and take a look at that. And then if we go to here, you know, I don't think it will.
Oh, dang it.
But you can just type in this right here. So anyway, the antiderivative is going to be 2x minus x to the third over 3 minus x squared over 2, and you integrate, or you evaluate the antiderivative from negative 2 to 1.
Okay, I figured it out.
How'd you turn it off?
Well, you have to go into format and automatically turn it off. So turned off the axes and then I changed the view to just,
Okay.
I went to zoom and it's standard.
Cool. So now we need the antiderivative at 1 minus the antiderivative at -2. So at 1, you're going to have 2 minus 1/3 minus 1/2. Oh, mama. And then at -2, you're going to have -4 plus 8/3 minus 2.
-6 plus 3/3. So it would be 3 1/3. On the other side, we're going to have 26. So whatever this is going to be 2/6 minus 4, so 3/6.
18 over.
5/6.
I think I had it right, didn't I?
So the solution here was Jerry. Having the two.
Yeah.
So it would be -13/6.
9 over 50.
So we have 7/6 plus 10/3, or 27 over 6,
Oh, okay. Okay.
or 9/2.
Why would we just do length times width? I think that would be much easier. If we were trying to find the area of two lines that intersect, two linear lines intersecting, can we do it that way?
They would have to give us a bound somewhere. There's 2 lines only intersect at 1 point, so they have to give us a
Something
bound
gave us a bound.
using some geometric formula.
Yeah, like if you use Pythagorean theorem to find the set of the two sides.
Yeah.
Well, Enrique, you kind of got trained, okay? We're gonna be like this.
Okay. Oh, you knew it was coming.
We're gonna have two parabolas that go like this and they make a circle.
Trigonometry.
Trigonometry may be my favorite thing in the world, and also might be my least favorite.
I think it's. I like it.
It sucked for as much as going through it.
I liked trig back in the days when it was like
When you were getting tricky with it?
when it was just sine, cosine, and tangent. It was
Yeah,
just
I'm like,
super
this
easy.
isn't too bad.
Yeah, I've got a calculator.
This isn't a problem at all.
Back in the side angle side days.
Like, all I have to do is plug in the sides I know,
Yeah.
and then solve for H, or A, or whatever the other was.
No trick changed.
Those were the days.
And then to find the area of the triangle.
Remember back when our hardest thing in math was memorizing the unit circle?
Yes.
Those were the days. We're trying to do times tables, all your times tables in 5 minutes. Oh, difficult.
I remember.
We were trying to find least common multiples and greatest common factors.
Oh, I love those.
What were those even?
There you go.
I love remainder days, where you divide and then it'd be like remainder 2.
Yeah, that was one of the best.
Yeah.
That's what I wanted to do.
The graphs of sine and cosine intersect infinitely many times, making regions of equal areas. You just got to find the area of one of these regions.
Oh, here's a no. That was violent vertical.
Remember when we learned about you can
I said, what are the
change
sine
the
graphs?
bottom to add and subtract them? I was like, this is
Like diagonal.
and it's
They do have those ones.
really change the bottom.
Wouldn't be a function.
So the sine function, you guys, starts at 0, 0, goes up to 1, down to -1, up to 1, down to -1, right?
Right.
cosine function starts at 1.
I know where the nodes and azimuths are.
It goes down, up, down, up. So we just need to find the area of one of these regions, because every region would be equal area.
I know you already accept defeat.
It kind of looks like DNA intertwined. You do a pretty good drawing. Even the lines you use, like the wires connecting them.
Yeah.
The melted bases.
It's because I'm a wizard, Jerry.
I was pretty funny. Pufflepuff. They should have said Pufflepuff. That makes way more sense.
It sounds worse.
Pufflepuff. Yeah, Huff is Puff. But
Okay, so any one of these regions, I just chose this one, but we need to figure out where these intersection points are. So we need to figure out where the sine of x is equal to the cosine of x. Where is the sine of x equal to the cosine of x?
where is it equal to?
Go home.
Okay, if you're thinking of unit circle, if you're thinking about unit circle, you guys,
Oh,
isn't cosine equal to x and sine is equal to y? Which angles around the unit circle have equal x and y numbers?
5/4.
5/4,
3 pi fourths.
and then 3 pi fourths are the same number, but one's negative, one's positive, so they're not exactly the same. So we skip 3 pi fourths and go down to 5 pi fourths. You following? Pi fourths and 5 pi fourths. Now that's just logically reasoning your way through this problem. If you don't happen to have the unit circle memorized, you could divide by cosine on both sides and have sine x over cosine x equals 1. What's the identity for that? What is it?
Tangent x.
Tangent of x is equal to 1.
Then you plug it into the calculator.
And then you do inverse tangent.
Inverse tangent of 1.
That's when you type it into the calculator.
Yeah.
And you type in.
And the inverse tangent of 1.
Would be
5 fourths. Or 5 pi fourths.
Now, your calculator acts as a function. You only get one input for each output. So it would give you an output of pi fourths, but you'd have to add pi k. You guys remember doing this last year in trig?
Yes. It was tricky. But we figured it out.
You kill him.
Okay, and it's this pi k that's the big deal. If k is 1,
Ooh, kill me.
then it's pi fourths plus 4 pi fourths, which is 5 pi fourths. So it would also give you the other answer. So it's pi fourths and 5 pi fourths. And then an infinite number of other intersections, but that's just all the rest of these here. We just need the pi fourths and the 5 pi fourths.
9 pi fourths.
Okay?
So would that be our
So those would be our bounds. So we're integrating from pi fourths to 5 pi fourths. Now, according to how I've drawn my picture, you got to look carefully. Which one's the above function? It'd be the sine function, right? The underneath function would be the cosine function. So you start with sine x minus cosine x, and integrate with respect to x. All right, now we got to speed this up. What's the antiderivative of sine?
negative cosine?
Negative cosine. Antiderivative of cosine.
Opposite sides of negative.
Yep. And then we integrate, or we evaluate the antiderivative from pi fourths to 5 pi fourths.
I'm here, I'm with you.
What are you guys? Focus top.
I was eating the ball there.
Hey, it really does help to be familiar with parts of the unit circle. 5 pi-4 is midway in the third quadrant. X and Y both have the same value there. In the third quadrant, they're both negative, and it's both negative root 2 over 2. Both for both sine and cosine. So the antiderivative of cosine is negative root 2 over 2 of 5 pi-4, but then it's negative.
Yeah.
So wouldn't that be positive?
Yeah.
Square root 2 over 2 minus negative square root 2 over 2. So that'd be 2 square root of 2 over 2, which is square root of 2 there. And then at pi-4, pi-4 is midway in the first quadrant. X and Y midway through the first quadrant is square root of 2 over 2.
Right.
So it's going to be negative square root of 2 over 2 minus another square root of 2 over 2.
Gives us negative.
But we're subtracting a negative.
So we're adding.
So we got 2 square
So
roots.
it's 2 root
So
2.
we have 2 square roots of 2.
Cubed.
Units squared, whatever the units are. 2 square roots of 2 square units.
That's a pretty small space. It's a pretty small area. Thinking about it in terms of numbers.
We think about it in terms of numbers. Yeah. But in terms of bumblebees, cake, ice cream, it's kind of like
You guys know that one time when I decided by giving you all pizza?
Okay, this one's going to be a bit strange. You guys like strange?
Yeah.
also I have 8 pieces now.
Actually, you know what?
So I feel very personally attacked.
That sucks.
Just a good thing I wasn't recording.
That would have been the greatest thing.
Oh, I still have to watch that video.
Just around 29 or 30 minutes into it, just disregard the comments from.
Start bashing it. Was that what it was, like 30 minutes?
It was about, yeah.
That's the only part I want to watch.
I tried to stick up for you.
Yeah, he was like, that's strike up. You were like, whatever, good, so.
Oh yeah, that's right.
You know, with friends like you guys, who needs enemies?
Right? Right.
Quoting, did you just quote Owl City?
Yeah, I do keep quoting Alice.
Is that Owl City's line?
Yes.
I've never even heard Owl City use that line.
They have. Because friends like
Don't lie. You don't listen to enough Alice City because they live
I only know 2 songs by Owl City.
you know, Twilight and
You know what I like? I like the person one.
Okay, now you guys, I need you to really listen carefully. This introduces a little bit of a different topic. There's a hard way to do this problem and an easy way to do this problem.
Too easy. Separate the variables, I would say.
Let's first take a look at a graph here. This graph, if you just subtract a 1, wouldn't you just have y equals x minus 1? I'm going to write that in red. This is just y equals x minus 1. Over here, if you added the y squared over and subtracted the 3, you have y squared equals 3 minus x. And then you'd square root and get y equals plus and minus. What's the problem with this? The problem is it's not a function. Okay. It moves 3 units to the right. The positive square root of 3 minus x looks like this. This is positive 3 minus x square root. The negative 3 minus x, or negative square root of 3 minus x looks like this. Negative square root of 3 minus x. Okay. You guys following there?
Yeah.
And then -1 plus x, or x minus 1, starts at -1 and it has a slope of up 1 and over 1, so it would look like that. It squeaked on the screen.
April Fool's.
Right. I need you to really listen carefully because a lot of students miss this point. If we're taking the integral with respect to x, remember how, I don't know, it was probably about 4 weeks ago, didn't we describe the area under the curve as rectangles?
Yeah.
Remember that? So if we consider rectangles going vertically, this would be integrating with respect to x. Okay? The problem is, if we take this rectangle and let's say I shift it over to here, and then I shift it over to here.
Your face is all different.
Well, the widths are different, but the point I'm getting at, which two functions do all of these three rectangles involve?
Negative.
It's the negative x, or 3 minus x, and then it's the x minus 1 function, right?
Yeah.
I need you to listen carefully. These three rectangles that I've drawn involve this function and that function. Would you agree?
Yeah.
But if we continue to shift to the right, let me draw one more rectangle.
Oh, then it's going to be using.
What about this rectangle here?
Both of the square root ones, and not the x minus.
Doesn't this blue rectangle reference this function and that function?
Yeah.
So we would have to set up a couple of different integrals in order to find the area under this curve if we're using vertical rectangles and integrating with respect to x. Okay? What if we switch this and did horizontal rectangles?
Well, that would be.
What would we be integrating with respect to?
Why?
Y. So let me see if I can erase some of this stuff here.
So what would it, instead of doing dy like you actually do, do you actually do dy?
Let me erase some of this.
That's scary.
There we go. So if we consider horizontal rectangles, okay? If we're going to integrate with respect to y and instead of with respect to x, it doesn't matter that this is not a function, okay? If we're going to use horizontal rectangles, this is where you really need to listen carefully. This sideways parabola is the equation x equals 3 minus y squared. And we don't have to solve it for y and get a plus and minus and have two different functions. We just have one equation, x equals 3 minus y squared. Okay? You with me? So if you can imagine that I took this blue rectangle and just moved it up and down inside this region, wouldn't that blue rectangle be referencing the same two equations regardless of where it is in that region?
Yeah.
Well, if that's the case, we don't have to change integrals because we're referencing the same two equations on the top and on the bottom, or to the right and to the left. You with me? So it would be much, much easier to integrate this function with respect to y and use horizontal triangles or horizontal rectangles. Okay? What we need to know is where does the graph intersect here and where does the graph intersect there, because we need to have bounds of integration. In the last problem we did, how did we find bounds of integration?
The two equations equal to each other.
So I'm not going to use the red ones because we solved for y in those cases. I'm going to use the ones we originally had. I'm going to take this equation, or that expression rather, and I'm going to take this expression and set them equal to each other. So y plus 1 equals 3 minus y squared. Add the y squared over, subtract 3, you're going to have y squared plus y minus 2.
And we already did that one.
Yeah, we did, didn't we?
Mm-hmm.
This is, make sure I get it right this time, y plus 2 and y minus 1. I know I'm moving pretty quick, I apologize, the bell's going to ring soon.
Oh, this class always goes way too fast.
I know. It's like running a marathon.
You sit down the next test. Y equals negative 2.
Every time. Just give me the A.
Yeah, Brandon's gonna get the A regardless. Brandon will probably ask to take the test still and be like, "Will you just use the score I earned?"
Yeah, he's gonna want to take the final 2 just so it can go on his grade.
So Y equals 1 and Y equals negative 2. Does that look reasonable just based on how I've graphed this?
For y to equal 1 and y equal negative 2?
Yeah.
Seems about right.
Okay, so now we know our bounds of integration. We're going to integrate from negative 2 to positive 1, but then we're integrating with respect to y.
Yeah, that's so weird to me.
Why would y get a turn?
Does that change our entire laws?
Same laws.
I just don't think y deserves a turn.
Because
It's not his turn. He's
now, instead of thinking of the above function and the below function, we need to think in terms of right to left. The function furthest to the right would be the above function.
Oh, this is so trippy.
This is when matrices come.
So it would be 3 minus y squared. This is the one. You guys follow me?
I'm not.
I'm with you.
And then we subtract the y plus 1 function because that's the one furthest to the left.
dy.
And we're integrating with respect to dy. Now here's a mistake students
I don't understand why dy gets a turn.
like to make. You see how I put the y plus 1 in parentheses?
Yeah.
Would there have been a difference had I not done that?
Yes.
Big difference. And that's a mistake students like to make. You've got to subtract the entire function.
Yeah.
That's a
Okay?
mistake we've been making for years, Mr. Hub.
So when you combine some like terms, you're going to get negative y squared minus y plus 2. Okay. Now the antiderivative is negative y cubed over 3 minus y squared over 2 plus 2y. We evaluate that antiderivative from negative 2 to 1. So antiderivative of the upper bound minus the antiderivative at the lower bounds, we're going to have negative 1/3. We keep getting the same values over and over again.
Yeah, it's so
Minus
tedious.
1/2
Basically, just gives us an equation.
plus 2. Yeah.
Yeah.
And then we're going to have positive 8/3 minus 2 minus 4
If it's 2 lines in a circle, it's just a point.
So negative 2, 6 minus 3, 6 plus 12, 6. Minus, so we have 8/3, that's a negative 6, that's negative 18. Thirds. Negative 5, 6. Plus 12/2, that's 12/6, sorry.
I'm expecting how it shoots.
No way, this is the same answer as before.
I told you it's because you did the same problem as both taken.
9/2.
Wow.
Is it always the same problem? So, what we learned,
Mr. Hub learned a whole new theorem.
it's 9/2 no matter
Area of
what.
every single region
If you
everywhere is
ever see
9/2.
any of these questions on AP test and 9/2 is an option, you choose it without hesitation.
Out, hesitation.
Without it!
What is hesitation, Cade?
I don't know, you tell me, Gabe.
I don't know. 'Cause